Hey guys, welcome back to Study with Me. And today we're going to talk about boiling points, which is a really important concept in chemistry. So, first we're going to take a look at some factors that will affect boiling points of certain substances. So, the first factor is forces. Forces between the molecules. Right? So basically, if the forces the interactions between molecules in a substance is strong, then the substance will have a higher boiling point. So we're going to talk about intermolecular forces here. So basically, that's like you guys have these molecules in a liquid, right? Okay, so the interactions between the molecules, the way they interact with each other, maybe there's like an attraction, right? That interactions we call those intermolecular forces, and it will greatly affect the boiling points of substance if the molecular weights are roughly constant. Okay, so when we talk about intermolecular forces, we need to take a look at 4 general types of these forces. So the first type is the ionic forces. So we can see these forces are present in salts. So let's take a look at sodium chloride, right? So you can see that, the sodium ion, is a cation, right? It has a positive charge, and the chloride ion, it has a negative charge, and these ions are attracted together by an ionic force, which is basically an electrostatic force. So this force is pretty strong, right? It's a factile. So remember that the ionic forces is going to be the strongest force that we're going to talk among the 4 types. Okay, so if we go down the ladder a little bit, we're gonna see the hydrogen bonding. Right, and this is present in alcohols or carboxylic acid and amines. So the hydrogen bonding, it's basically, let's take a look at a water molecule. We can see that our oxygen atom here is very electronegative. So most of the electrons will gather towards the oxygen atoms, so it will have a partial negative charge, and the hydrogen will have a partial positive charge. And because oxygen is really, really electronegative, so the differences in the charge here is really large. So if we have another water molecule here, we can have like an attraction between this oxygen atom and this hydrogen atom, and we're going to call that hydrogen bonding. And remember that this occurs with not only oxygen but other 2 really electronegative elements as well. So we're going to take a look at fluorine, oxygen, and nitrogen. So next, it's pretty similar to hydrogen bonding, but it's weaker. So we're going to call that dipole forces. And we're going to see this in, carbon with some electronegative groups. So the X here can be oxygen, nitrogen, chlorine, and so on. So this is basically, it's pretty much the same thing, but it's weaker. So actually, hydrogen bonding is a type of dipole forces, but it's stronger. Okay, and the last one is going to be London dispersion forces. So this one is present in all molecules, but they're the most prominent in hydrocarbons since they lack the previous three. And actually, the London dispersion forces, we're going to talk about the polarability of a molecule. So it's actually increased when the molecular weights increases. So the larger the molecule is, the stronger the London dispersion forces is. But this one is the weakest, right? It's the weakest among the four. So if we have to rank these forces in terms of strength, then ionic forces would be the strongest, and then hydrogen bonding, and then dipole forces, and then lastly, London dispersion forces. So normally in an exam, you can expect a question looking like this. So it would give us like 4 substances. 4 molecules looking like this. Okay, let's call this A, B, C, and D. And it's going to ask to rank these molecules in terms of boiling points, in terms of increasing or decreasing boiling points. And how are we going to do that? So we need to look at other factors as well. So the next factor is size. So remember that increasing number of carbons is going to be means increasing boiling points. So when the types of forces constant, boiling points will increase with an increasing number of carbons. And I'm going to take a look at some example. So here I have butylamine. And here I have propylamine. And here I have ethylamine. You can see that, this one has the highest number of carbons, right? This one has the second largest number of carbon, and ethylamine has the lowest number of carbons here. And actually, in reality, the boiling points of butylamine is 351 Kelvin. For propylamine, it's 322. And ethylamine, it's 291 Kelvin. So we can clearly see that this is the direction of decreasing boiling point, right? And is also the direction of decreasing number of carbons. So yeah, you can clearly see that the three molecules are very similar to each other. So the forces on them is basically the same type of force. So in this case, you can see that the number of carbons really have strong, is really prominent when we have to determine the order of decreasing boiling points. So, and lastly, another factor that we need to consider in order to determine whether a substance has a high boiling point or low boiling point is the surface area. So, increase in surface area means an increase in boiling point. And why is that? So with the type of force constant and molecular weight constant, boiling point increases with increased surface area. So let's take a look at a few isomers of this. Okay, so let's take a look at the three isomers. Okay. Pentane. Okay. You see that this is kind of like a linear shape, right? And here it's branched. But here we can clearly see two branches here. So it's like highly branched. It's much more branched. You can see that. Well, this shape is going to have larger surface area. And why is that? When we take a look at this highly branched pentane, we can. I'm sorry, it's actually not pentane. Is okay. Oh, this is actually neopentane. So when we take a look at this highly branched molecule, we can see that it's going to be the most sphere-like, right? It's going to be the most sphere-like. So we already know that a sphere is a shape that is going to have the smallest surface area. So this one will have the smallest surface area, right? And in reality, this has the boiling point at 310 Kelvin degree. This one 300 degree, and this one at 283 Kelvin. Okay. So you see that this is in the order of decreasing surface area, but also in the order of decreasing boiling points. So, next. And now we're going to learn how to recognize these the forces in the molecules. Because, if we have to rank some molecules in terms of lowest point, decreasing boiling point, or increasing boiling points, we need to take all those three factors into consideration. And then one of the factors are the forces, and we really need to know how to, recognize the forces inside a substance. So first, let's talk about ionic forces. So it's actually the attractions between point charges. And, let's take a look at these substances. So, well, the first thing to look at. So, if you see any point charges drawn, so like this or like this, it's a telltale sign of ionic bonding. But however, if you don't see that in drawings, like in this example, well, then this exists. So the thing is that you see the electropositive metals, such as sodium, potassium, lithium, and magnesium. If you see these four highly electropositive metals, and if they're bound to a very electronegative atom, such as oxygen or nitrogen, well, that's a telltale sign too. So here we can see that oxygen is being bonded with here sodium. So that's a telltale sign that this is definitely going to be an ionic bonding. And here too, even if the charges are not shown, but we can see that oxygen here is being bonded to sodium. So this one is an ionic force. So next, let's take a look at hydrogen bonding. So how do we recognize hydrogen bonding inside molecules? So well, we need to look for molecules containing OH bonds, or the bond between nitrogen and hydrogen. Because, we need to keep in mind that the electronegativity of oxygen is 3.4. Nitrogen is 3.0, and for hydrogen is 2.2. So the differences between the electronegativity of oxygen and hydrogen and nitrogen and hydrogen is pretty large, but not large enough for the attraction between them to be ionic. So it falls right inside the the range that it's perfect for what we call hydrogen bonding. Okay, so let's look at, so it's pretty evident in alcohols, right? So let's take a look at this. This is ethanol, right? You can see that we can see an OH group right here, and it's exactly what we're looking for, right? So this molecule will have hydrogen bonding. And carboxylic acids, such as this one, also falls into this category as well, because you can see that here is an OH group, right? So we will have hydrogen bonding for amines, such as this one, or this one. As you can see here, this is, you can see a nitrogen, and hydrogen bond here, and in here too, right? That's like 2 bonding that falls right into this category. So yeah, it also satisfies our hypothesis, and they will have hydrogen bonding as well, right? However, between these 2 types of hydrogen bonding, they really have different strengths. So the hydrogen bonding OH is stronger than the hydrogen bonding with nitrogen and hydrogen. This is because of greater electronegative differences between oxygen and hydrogen when compared to nitrogen and hydrogen, right? So you see that the differences between oxygen and hydrogen is larger, right? It's going to be like 1.2, and for nitrogen and hydrogen, that is just going to be 0.8. So because of the higher differences in electronegativity. I'm sorry, I kind of like misspelled it. Differences in terms of the electronegativity. The OH bond is going to be stronger than the NH bond. So next, let's take a look at dipole-dipole forces in general. So this is how to recognize them. Look for bonds between carbon and an electronegative atom, such as, so for the X here, that can be oxygen, that can be nitrogen, and that can be halogens, such as fluorine, chlorine, bromium, and iodine, right? This is a telltale sign. So you can see this clearly in ketones. When we have a functioning group here, you can see that this is carbon bonding with oxygen, right? So it will have dipole-dipole attractions. And even with other groups such as ethers or esters and aldehyde, you can clearly see the bond between carbon and oxygen, right? And even in amine's group, right, this is the bond between carbon and nitrogen. And moreover, we can also see this in alkyl halides, where we can see that the carbon here is going to bond with halogens like this. Okay. However, all of those attractions are weaker than hydrogen bonding because the electronegative difference between carbon and oxygen or nitrogen or halogens is not as large as the difference between the electronegativity of oxygen and hydrogen, or nitrogen and hydrogen. So since the partial charges are smaller, the intermolecular forces are weaker, and the effects on boiling point is smaller than that of hydrogen bonding. So next we're going to talk about the London dispersion forces. So this one is the weakest. So it's actually the attraction between instantaneous dipoles and generally non-polar atoms or molecule. So basically, let's take a look at argon. these are absolutely non-polar, and they're not going to bond with each other. They're noble gases. But however, when we smash them all together, they can have an instant dipoles arise, right? Just in an instant moment. So this partially positive will be kind of like attracted to this partially negative part, but in just an instant. And this one is present in all atoms and all molecules. So, however, since it's really, really weak, it's only significant in hydrocarbons, since the permanent dipoles are generally very weak. So let's take a look at this. Right. This is benzene, right? And yeah, you can see that now it's going to have London dispersion forces because it's a hydrocarbon. And it lacks all the previous three forces. So our LDF, which is, London dispersion forces, will be the most significant here. So, however, the strength of the interactions between molecules increases as a function of the surface area. So a really large molecules like this will be more polarizable than a small molecule like this. So the London dispersion force of this is larger than that of this small molecule. So here we need to, so the trend for this is that an increase in boiling point means that an increase in molecular weight. So the larger the molecule is, the higher the boiling point of that substance is. Okay, so let's take a look at some examples to really know how all of those theory can be applied to your exam. So I'm gonna give you guys these 4 molecules. Oh, I'm really bad at drawing. Okay, so here we can see that the structure of these molecules, well, they are really different, but they have something in common, which is this benzene ring. Okay, so we look for, so you see that, these molecules will not be much different in terms of molecular weight, because, you can see that their structure are pretty similar. They all have one benzene ring. So we're going to take a look at the forces present in each molecule. So in this molecule, in A, we only see, it's absolutely not polar, so we can only see London dispersion force here. And here we can see that here is an OH group, and what is that going to tell us? That we have hydrogen bonding. Right? So we only take a look at the strongest force present. Okay, so next here we have, this is carbon, right? Carbon bonding with oxygen. And that's going to mean that we're going to have a dipole interaction. And in D, well, this molecule is also nonpolar, so we only see London dispersion force. So, oh wait, we see two molecules with the same type of force, and how do we rank these? Which one has a higher boiling point? Well, we can see that in D, well, the molecular weight would be larger than in molecular A, right? Because we have more carbon here, like some extra carbon. And also, when we talk about the surface area, it's also going to have a larger surface area as well. This one is more sphere-like, so it's going to have smaller surface area. So when we have to rank these in terms of decreasing boiling points, it's going to be, hydrogen bonding is the strongest force, right? So it could be B, C, D, and A. A is going to have the lowest boiling point. Okay, well, let's take a look at another question. So here, we're going to take a look at which one has the highest boiling point. So for A, this is A, this is B, this is C, and this is D. So again, we're going to take a look at the forces present. And in A, we have hydrogen bonding, right? We can also see dipole, right? Right, because of the oxygen here bonded with the carbon, but since hydrogen bonding is stronger, we're going to take a look at. We're going to keep this in mind. In B, we can see that oxygen is being bonded with carbon. So it will have dipole. But it will not have hydrogen bonding though. So in C, we can see that we also have dipole, right? But, well, we see two oxygen here, and so, it's going to be a little bit more polar than B. And in D, it's non-polar. It's just a hydrocarbon. So we only have London dispersion forces. So we can only see one molecule has the strongest type of bonding between these among these three, which is hydrogen bonding. So we need to choose A for this question. So A is going to have the highest boiling point because the intermolecular forces between the molecules would be the largest due to the hydrogen bonding. Next, which is another ranking problem, we have, this is our first molecule. This is our second molecule. This is our third. And this is the last one. D. Okay. So in A, we can see this OH group, so it will have hydrogen bonding in A, right? We can also see dipole. In B, we see, would you see anything here? Sodium and oxygen. Oxygen is really electronegative element, and sodium is really electropositive. So actually, we're going to have the strongest force out of them all, the ionic force in here. And we also have dipole-dipole. Obviously, we're going to have LDF because that's like present in all molecules. So here, what do we have? Oh, we won't have hydrogen bonding nor ionic forces. So we only have dipole-dipole. And obviously LDF because every molecule has it. And here we have dipole-dipole. I'm sorry. We're going to write hydrogen bonding first because that is stronger. And LDF. Okay. So first, because the ionic force is the strongest out of them all, so obviously, in terms of ranking them based on decreasing boiling points, B is going to have the highest boiling point. B is going to have the highest boiling point. Okay, so now let's take a look at A and D because they have the same type bond. However, when we take a look at the molecular weight, we'll see that D is larger, and moreover, we'll see that it has more hydrogen bonding because this has 2 OH group. This one only has 1. And it even have more dipole-dipole attractions because it has 2 CO bonds. This one only has 1. So D is going to rank in second place, and then A, and in the last place is going to be C. Okay, next. So we have 3 substances here. This is A, this is B, and this is C. We can see that, in C. We can see that, well, A and B will have the bond between nitrogen and hydrogen. So these two have hydrogen bonding. However, in C, there's no bond like that. So we really have dipole-dipole. But, so now, so obviously, C is going to rank in the last place. But, now let's take a look at the A and B. How do we determine which one has a higher boiling point? You can see that, well, in A, we're going to have 2 NH bonds, right? So we can, this NH group by NH2 can be written like this. Right? So they have 2 nitrogen and hydrogen bonds. So while in this one, it only has 1. So yeah, the hydrogen bonding in between the molecules between A is going to be larger than B. So A is going to have the higher boiling point. Right? So that's basically everything that we need to know. Oh, well, in this level, I'm talking about the level of the question you may encounter in the AP chemistry exam. So, however, if we have a question like this is A and this is B, and it asks us to determine which one has a higher boiling point, then it is actually really hard to predict since even though B has hydrogen bonding and A only has London dispersion forces, the molecular weight is larger, much larger. So this is way too hard to predict. And in this case, I think the best way to determine is actually going to conduct some experiments. So, well, in questions like this, well, we cannot predict. But however, in most questions, when the structure of the molecules are pretty much similar, we can use the things that we just reviewed with each other to, well, just kind of like predict the order of the molecules in terms of decreasing or increasing boiling points. So this is the end of the video. Make sure to subscribe to my channel for more videos like this. I think it's time to say goodbye now.